let's talk about how a PLC does its job. We've covered the physical aspects. So the programming language is commonly referred to as RLL, relay ladder logic. And relay ladder logic, this is the electrical schematic for this panel. Okay? And as you can see, we have rungs, and we have these main connections, all right? And this is a typical wiring diagram. This is the plus power for the DC, this is the minus power, and if I go to the first page, I have the exact same style of wiring diagram where the 120 volt power comes in through a main switch and feeds this line going down and feeds across to the things that run on 120 volt power. What runs on 120 volt power? My two power supplies. And the air compressor motor is down in here, and we have an e-stop contact through it. All right. So you can see that's what the wiring diagram, you know, the physical wiring looks like. So here is part of the program in this machine. And as you can see, it looks a lot like the wiring, relay ladder logic. So what they did, one of the reasons that the PLCs are popular in controls is because once the controls are in a plant, it's the maintenance guys that have to take care of it. And the maintenance guys have to be able to troubleshoot it and figure out if there's a problem and so forth. So by making the programming of the PLC look exactly like the wiring diagram that the old timers were familiar with, you know, because and still have in the plant that to troubleshoot, made things a lot simpler because then they didn't have to learn another language. And one of the things, it occurred to me the other day, there's a lot of talk about other languages being available on the PLCs. And it occurred to me that one of the big advantages of the PLC programming language is it's visual. We draw this on screen. And that's how we program. We have the screen starts out with two vertical lines, and we put rungs between them, right, to make things happen. And that's very, very visual. And it's not like C++ where you have these really arcane syntaxes, and you know, Python has an arcane syntax, and Visual Basic has an arcane syntax. And so those languages, you can't look at the programs from any of those and get an instant understanding of how it works. Whereas with the PLC, you can't. You can look at it and say, oh, I see what's going on. And when we hook up a laptop, the programming laptop to the PLC, not only are we able to see the program, but we're able to see what's on. So it changes the color and shows us what parts of the program are actually active. So when you're trying to troubleshoot, you say, oh, you know, you're looking at this now. Now this happens to be an equal contact, right? Which is an equal contact is comparing numbers. So this is comparing a number to 0, saying if it's 0, then do something else, okay? Now, if it's 0, if this is actually 0, then this will be lit up, and you'll say, and to indicate that yes, this rung is able to work. So you just go down the rungs looking for where it stops, okay? And that's how the troubleshooting works, and that's exactly the way you troubleshoot the wiring. Because when you troubleshoot the wiring, you go from the power source, you go through the fuse, you check the top of the fuse, you check the bottom of the fuse, you follow where it's going until you find something that's off. And that's the troubleshooting method for wiring, and it's exactly the same method for PLC. So troubleshooting is very much easier as a result, okay? Now, also, and I didn't mention this before, but where inputs come in and where outputs come out is kind of, you don't really care. In other words, if I was in a hurry and I had somebody helping me, I'd say, put all your inputs to here. and put all your outputs there. I'll figure out where they are later. And that's quite common that you do that, because internally you can connect anything to anything with no problem whatsoever. So it doesn't matter. So there's I have a convention of my own of what I connect and where, but the reality is it's just a convenience thing. And mostly what it's about is when I get to the wiring diagram, and so here's a wiring diagram, and this is inputs, right? So I have a block that indicates the module that's in the PLC. It's actually, this is part of the PLC, but it's logically one of these connectors, right? So each block is a connector on the PLC. And so that is this shows you the connections from various devices. These are inductive proxies that are going into a digital input, all right? So I can put them anywhere, but I tend to, in my electrical drawing, tend to group things in a certain way. Like, for instance, all my proxies are on the same block. And as a consequence, I also tend to put like a fuse for each of the connectors, so that if there's a problem, if you got a bad sensor, it might blow the fuse. But by keeping the fusing like this, right, where I have a fuse to each of those blocks, I would blow a fuse that turns off those 4 modules, and I'd know right away where the issue is. It's got to be one of those 4. At a previous job, I went out to a waste treatment plant, and the entire plant was running on one fuse. And one sensor went bad. And this plant had 30 or 40 sensors. And so I had to go in and lift wires until I could make the fuse hold. There's no other way to troubleshoot it. So that's why I wind up, for me, fuses are a troubleshooting tool. So it makes it easy to get it up and running. And a big part of it is that a lot of what I've done has been, my customers have been remote all over the US. And so you're not just running down to the customer to take care of their problem. You're going to have to solve it over the phone. And so this makes it very much easier. You can pull a fuse and say, you can tell them, look, oh, that sensor's not working, go look at this fuse. And there it is, you know. And then it might not be that sensor, it might be another one that's tripping the circuit, and you know, but the sensor you really need it is off. So yeah, so it's more about remote troubleshooting than anything. Yeah, you know, you don't want to travel 1,000 miles and to go fix something that could be identified quickly.